Okay, so internal energy is the other name for thermal energy. It's basically the sum of all the energy of the constituent particles in a system. And we represent that with a capital U. So for me, it would be the energy of every single atom in my body. You take the kinetic energy of them moving around and any type of energy they have stored in like movement, in how their bonds go together, whether they move apart and all that kind of stuff. Sum it all together, and that's going to be the internal energy or the thermal energy of my system. So one thing that a lot of people tend to have trouble with is distinguishing between heat and temperature. So we need to make sure that we know the difference. So let's clarify. Heat versus temperature. I'm going to start abbreviating. So temperature is the average kinetic energy of molecules within a system. Whereas heat is the total energy of molecules within a system. So that would be like if temperature, that's going to be the average grade in a class. Heat is if I took all of your grades and added them together. Big difference. My apologies. This one right here should be internal energy. Internal energy. I should have noticed that as soon as I said it. So this is internal energy. And now we have heat. So heat, remember, heat is specifically talking about the amount of energy that flows from one thing to another. So it is the energy transferred from one object to another. And that's basically in any form other than work. All right, so if I give you this problem, I want you to tell me which one has a bigger temperature and which one has more heat. So let's say I've got a sample of iron. Here's my sample of iron. It says Fe. And then I've got another sample of iron over here that says Fe. This guy weighs 1 kilogram. This guy weighs 2 kilograms. This guy has a temperature of 30 degrees Celsius. This guy has a temperature of 30 degrees Celsius. I want you to tell me, if we call this system 1, system 2, how does T1 compare to T2? And how does how does U1 compare to U2? So greater than, less than, take a second, think about it. Beep, 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 boop. Look at that, they have the exact same temperature. Incredible. But because there's more object here, there's more total energy, the particles are all moving on average about at the same speed from this side to this side, but this one has twice as many particles, so there's way more heat trapped in that one. So now let's look at the formula for it. Our formula for internal energy is just going to be equal to the number of particles times the average kinetic energy of a particle. That's a pretty simple way to do it. If you guys have taken chemistry, some of these ones I'm about to write may look more familiar. 3 halves n kBT. Big N represents the total number of particles in a system. Kb is the Boltzmann constant. That's going to be on your equation sheet. Temperature is going to need to be in Kelvin. Cool? And then over here, where we have 3 halves nRT. which are another constant. That's going to be the rate constant for this. And again, T still has to be in Kelvin, but little n is going to be the number of moles in a system. There we go. And then for the last part, these equations we use work only for what's called an ideal gas. So real versus ideal. In a real gas, we have, like let's say we have a diatomic atom. Normally, we're only looking at the kinetic energy, thinking of them as like billiard balls where they move around, they bounce. Anything they hit, they store energy. But what can happen is when we have diatomic atoms like this, some of the energy can be stored in the bonds. So if this were to hit a wall, think of that as like a spring in there. If they're both moving together without springing, when they hit the wall, that spring can compress, contract. Some of the energy can be stored in the bond between them. So this isn't exactly true where temperature is only looking at the kinetic energy of them moving around. Some energy can be stored in there. So most gases that we're going to deal with are diatomic, and they can store energy like that, but we're just going to treat them like they're ideal for what we're working with. It's way more work to start getting into that complicated mess. So the rules work better for monatomic gases, like all of the noble gases, but still, for what we're doing, we're just going to treat everything like it's a monatomic ideal gas.